This is not going to be a very technical talk. I can answer questions about our LLVM compiler, which is, but I really wanted to use the opportunity to talk about some of the upstreaming activity that a colleague of mine, Jan, is working on regarding device libraries for GPUs, right? So, so some background, we all know GPUs are now, and accelerators are now a mainstream part of HPC. But highly tuned architecture-specific libraries, they've also been part to HPC, important. So the question that we ask is, how can we seamlessly manage device libraries to support offloading languages, such like OpenMP, HIP, CUDA, and OpenCL, which, by the way, are all part of the Clang LLVM infrastructure. So that's what I really want to talk about today, is how we can do this and what's necessary. But before we get into it, I want to talk about what I really mean by a device library. There are two types of GPU libraries. One are kernel libraries, and there's what I would call compiled kernels, right? Where you have a grid programming language like HIP or CUDA or OpenCL. And then you also have an API that you use to launch the kernels, pass data to the kernels, to create and manage those kernels, right? Then we're also seeing kernel libraries that are wrapped kernel libraries. So essentially where you implement using a grid language like the first one, but you actually eliminate or minimize the need for the grid language by making the API directly available to the application user, okay? You have limited functionality with this, but it is a lot easier to use. But the other type of device library is what I'm going to call a device function library. Just actually settling on a name to call this thing. But these are simple libraries or functions that kernels call or that it can link into. We're going to call it, when I wanted to call it device link library, the acronym was DLL, and that just didn't work, right? So Jan said, hey, why don't we just say a device function library? So a good example is an intrinsic math library, something that you always need, things like square root, etc. That's an example of a device function library. This is really important to OpenMP target offload, and I'll explain that on the next slide. But I wanted to tell you, this talk is really just about device function libraries, not about kernel libraries. Okay, so let's talk why we need these device function libraries. And this is a really short introduction to OpenMP target offload, right? It removes the need for GPU grid launch and management API. Essentially what you do in a target and offload environment is you mark a section of code as the target region, and the compiler auto-generates a GPU code for that arbitrary code section. And within that code section, you have parallel constructs like parallel 4, distribute parallel 4, and SIMD. You have all of those constructs within the target region. So the OpenMP runtime actually then, once these will manage and launch these auto-generated kernels using the libomp target runtime. So my question is, let's go back to devices. What happens when a target region code references a function that's not in the user source code? You basically get an unresolved reference during linking of the auto-generated GPU kernel, right? So it's not in your code, it must be somewhere else. So any kind of glibc function, for example, you're going to get an unresolved reference. So what we need is device function libraries to increase the functionality and even the persistence, if you think about it, of target regions in OpenMP. Device function libraries are also usable by the kernel level languages. Since it's callable by a kernel, you certainly could use a device function library as to extend the capabilities of your HIP or CUDA kernels. Now, one thing we notice is that most people prefer the same name and interface for functions in a device function library as you have in a host library. And for OpenMP, we actually need this because it's required when something occurs that says that target region cannot run on the GPU. It has to fall back to the host. So that interface needs to be very similar. So let's talk about the current management of device function libraries, right? Right now, today, what you see is bitcode files. We also see recompilable source code, like include libraries. And in some cases, in the case of NVIDIA, you have the ability to have a link library of kubins. So that's what we have today so far for these. But I want to ask the question, okay, so now I want to take a quick review here, very simplified for demonstration purposes. And I actually, this presentation will go rather quickly, so I can stop and answer questions if you have them. I just don't see the chat right now, so you'll have to, interrupt me. So a quick review of how host static libraries work, right? Where you compile something into an object file and then you archive that file, the bar.o, into an archive file, the libfoo.a. And this is very simplified. Of course, there's ranlib and a couple other things that you might want to do for optimization. But these are essentially the first two steps in creating a library. And then, of course, when you use this library, you say, compile and you say -lfoo. Now, there are also other arguments, environment variables, and things to help an application find this library, okay, like -big L and library path and run path. That's just a quick review of what's happening with hosts. So the question is can we make a consistent way of dealing with device function libraries as done on the host, right? So let's go through those three steps again, right? The first one is compiling a function that you want to put into a library. When Clang with some offload options, and then you create an object file called bar.o. And this actually works today, right? We can do this, and that bar.o has stuff. You're going to use the word stuff a lot here because stuff could be a couple of different things, but it has stuff from the device paths, because when you're using offloading, you're going to have the Clang compiler is going to have multiple passes across your code, and you're going to end up having host object and then embedded into that device code, right? So the Clang developers, we call this today a bundle, all right? There are bundling tools in the system, but essentially you get a single file that's a bundle. So multipass compilers allow the source code variation to optimize for specific GPUs. So that stuff that you have in there for the device could actually be tuned specifically for an architecture. Today, okay, thanks to stuff that happened over the last year, a Clang bundle is actually a host object with the device stuff tucked into an ELF section. And I'm losing my, okay, can't see the symbol information is in a bundle today is host specific. So we're actually good in terms of doing building a device function library with the first step. So let's talk about the second step. We build our library using the archive command. It turns out this works as well. But where did the device ELF sections go? They're still there, but they're ignored at the host link time. So that's kind of where we're at. I mean, this all works. You can get a nice archive file, but it's not very usable, right? I want to take an aside here, and before I go on to talking about step 3, that archive file that you saw created, I'd like to come up with a name for that. And I know in discussions with Ravi and the multi-company meeting on LLVM, we've heard the term FAT library, tried to use the word heterogeneous library. I'm trying to converge on this term offloading library because that's actually a Clang term that is more politically correct, by the way. But Clang uses the word offloading tool chain in the development. So I wanted right now, for the time being, call this an offloading library unless somebody comes up with a better name right now. So remember, the offloading library could actually have stuff for multiple device types, because it's not just one device. It could be the host plus each device that you're concerned about. Right now, the offloading library is static, but the concept could extend to shared objects in the future. All right, so let's go to step 3. What happens? All right, step 3 is the user actually using this foo.a, right, or libfoo.a, which got created in their application. Well, what's going to happen? You'll get an unresolved reference during the GPU link phase if the application was OpenMP and referenced the function. You'll just get an unresolved reference. And the reason why is we never got the stuff out of the libfoo.a. So the answer is no. we can't make it consistent. GPU linkers currently don't understand what to do with a offloading library, libfoo.a. We need a tool to extract the device stuff to make it usable for GPU linkers. Okay. So let's talk about GPU linkers like NVLink, like LLD, and even LLVM link, right? Or even there's even a post-Clang link we called M-link as an option in Clang. So today, you can have a bitcode file or an LLVM IR file. You can also have the HSA or the instruction set architecture binaries. In case of NVIDIA, it's called the CUBIN. In case of AMD, it's called the HSA code object. We could even just today give the .o file to the linker, and it turns out the current Clang toolchain knows about this and will actually unbundle it, right? But also don't forget you can put stuff, a lot of people do this today, or they put their library or their code that they want in source form as a .h or HPP file. So why can't we use a .a or shared object with the symbol information for devices? Because this is what the host linkers are doing, right? So in our example, the libfoo.a, it actually has, from the perspective of the device linker, mostly useless host symbol information, okay? The question is, can we create a device-specific archive library with useful device symbols, right? So this is really picking up in speed here. So feel free to stop and ask a question. So I'm going to introduce this term, device-specific archive library, or DAO, right? And it's an archive file made from similar device-specific objects. There'd be bitcode, CUBIN, HSA code object. It's not the offloading library. The offloading library is this FAT library, right? That has both the host and device. This is a library that has just specific things for the device. And to use this, I've listed some things here that we're working on that are needed to LLVM to make these DAOs useful, right? The first one is fairly simple, right? Enhance LLVM link to use archives of bitcodes, in addition to individual bitcode files, right? The patch for that is currently in review by my colleague Jan, and it turns out that the Clang or the LLVM class library supports archives already. It's not necessary. It's fairly easy to do that. So I'm kind of surprised that we haven't had this enhancement to LLVM link done in a long time, right? So it was a fairly simple enhancement. The second thing we need is some tool, right, to extract the DAO from the offloading library. And Jan has a patch for this that's ready to review. Thirdly, we want to change the Clang driver to insert the above tool to extract the DAO and provide that DAO to the GPU linker, because now we can deal with that from step one. So, I'm going to show a picture of that next and come back to this page, because there's a lot of notes on this page. So I'm going to show the diagram here. Hopefully we didn't cut too much off here. So this is the Clang driver flow with the offloading library. So the first is the compilation, the user compilation of his code. And of course, when he's compiling his code and he wants to reference the library, he typically needs a header. So you say -i foo.h, right? And then essentially what that happens is the output of that compilation will be a bundled object, right? That will contain typically host or the CPU object code and device bit code. And then the next step, we take a couple of bundled objects, x.o and y.o, and we want to do this linking. Now, there's a lot of boxes down below, but really, I want you to just look at the edges for a second. We have our user objects on the left, and we have an offloading library on the left. In the end, we want to do a link and get an application. But because we have GPU code in this, we have some complexity. So that's essentially what we want to do here. So this red arrow here represents what's new, this new tool, Unbundle Archive, which, by the way, we're building as an enhancement to the current bundling tool. So this tool up here that bundles, it's internal to the Clang environment, right? Users don't need to know about these green boxes. But internal to Clang environment, the bundle tool, the unbundle tool, and now the unbundle archive tool are basically using the same binary with just different options, right? So what will happen is, if necessary, the extraction will be pulled out of the offloading library here, libfoo.a. And the reason I say it's if necessary, it's very possible that you may have actually already created a device-specific archive library. One good example would be something like the lib OMP target -NVPTX-A, right? Let's go back up to the screen here, the former one here. So an offloading, you can actually extract from an offloading library and can generate a permanent file, or actually you can create the permanent file with other tools, right? And an unintentional example of an existing DAL is the lib OMP target -NVPTX. And by the way, this is, we basically took this as part of the convention, right? So the convention is, this is an architecture specific device library that contains, in this case, code for the ISA linker, which would in this case be CU bin. So the point is that an offloading library could actually be a single file, and it also could be a collection of device-specific archive files, right? So the Clang driver must find these permanent files by establishing a naming convention using this similar search mechanisms that we had with the host libraries. So the naming convention that we've created is perhaps too hard. If we have time, we can go into it a little bit more. But the naming convention allows for an ordered search, because in the case of GPUs, we want to often look for a library implementation that has stuff for a very specific GPU. And then you want, if there isn't a library that exists for that, you want to look for something that's architecture specific, NVIDIA versus AMD, for example, right? And then the possibility of a generic DAL, if it's bitcode, it could actually have nothing specific to anything in the GPU. So of course you still have to look for those. If none of these are found, then the Clang driver will generate that existing call to the extraction tool. So I'm back to this chart here. And that search in the Clang driver is done, is marked as a #1 here, right? Where if there exists permanent files that have that in it, they will be found and supplied here. And then the extraction from the traditional host library is not necessary. But if they're not found, which is often the case, right, we'll extract the DAL, and the DAL will be provided to the device linker here. It could also be provided to the ISA level linker for the device. In this case, that could be NVLink. In the case of AMD, it's LLD, right? Now, what about the host linking, right? The offloading library, remember I said earlier, it's in the format that's necessary, that you can give directly to the host linker. So there's no reason to do anything at all with libfoo.a when passed to the actual host linker, which is here on the far right. Okay, so a lot of complexity here, right? Essentially, we're doing LLVM linking with here, and then LLVM optimization. We get our final device bitcode that's passed to the back end, right? Which could be generating PTX out of here, or it could be generating code for, in the case of AMD, it would be generating HSA code object. And then that goes into the device linker, and then the device linker passes its ELF to the final application binary, right? So essentially, if we get these pieces upstream, and I guess that's the real purpose here, is to lobby for those. I don't think we have to lobby too hard. Jan's done a pretty good job implementing those. We'll have a seamless way to manage offloading libraries in LLVM that's consistent with host libraries. But my next question is, what about source language for writing offloading libraries? And I want to say that those library creators, those people writing those are our real heroes, because they have to understand typically the architecture that they're building their optimized library for, right? So recall, our first step is to just say of building a library is we compile to create an object. But I would like to encourage people to actually use OpenMP, OpenMP5, because there's some features in there that create bundled objects, make it easy to create a bundled object from a single source. So without getting into too much detail, I'm just going to show you these two examples. This first one here, where we're just using OMP target, declare target. In this case, we have the same name, the same interface for the users for the DAXB, and it's the same implementation, right? Which is, so for both the CPU and the GPU, this is, you're going to compile this function increment OMP, and it's going to take an index and actually increment that array index by 1. Right, so that's how declare target can work for you. When you compile this, you will actually get a fat object that you could actually use to build your archive, your offloading library. The next thing on OpenMP is the OpenMP declare variant. In this case, what we're showing is the Saxby operation. The user will still use the same name, the same interface, but depending on the context of execution, you'll have different implementations. If used in as part of a declare target that's being executed for the AMD environment, it would run this code right here, and that would cause it to use the OMP Teams Distribute Parallel 4, and which, by the way, is the same for NVIDIA. Okay, but in the case of the host, all we want to do is an OMP Parallel 4. So this is how, you know, you can actually, with the declare variant, which, by the way, is a lot of options and very, again, it goes, you need the hero programmer to really understand all the things that you can do with declare variant. But this is not something that the users are going to do. This is a component of the offloading library, right? So we're really trying to make the same interface for the users. So here's the summary of my talk, right? There is extensive use today of kernel libraries, but device function libraries are needed to build more functional kernels for OpenMP, and as well as the grid programming models, right? A device function library is an offloading library, or it's actually multiple device-specific archive libraries, right? Offloading libraries with auto extraction to DAOs provide a consistent user experience. What I mean by consistent is consistent in construction, consistent in the user compiler command interface, like finding the libraries, and it's also consistent in the source call site. And the last point I want to make is OpenMP5 provides features to simplify the programming for offloading libraries.